Okay, my name is Dan Low. In this video, I'm going to talk about the applications of PCP post-correspondence problem. Specifically, I'm going to talk about the problem LG equal to MT is decidable, given the G is context-free grammar, and whereas LG is the sigma star, it's not decidable. Okay, and another question I will be talking about this video is LG is a subset of LR. R is a regular expression, and G is context-free grammar, and this question is decidable. Whereas if you flip over the R and G, okay, then the question to ask if the language LR is a subset of LG is actually not decidable. So let's start it. So we start out with the some facts about PCP. Okay. So first of all, PCP is undecidable. Okay, and to prove that you can reduce LU, which is known to be undecidable. So LU is reducible to PCP. Okay, and I'm not going to prove in this video because it's gonna be quite long. Okay, and PCP, the problem is basically given a PCP instance, A sub B, A is a list, B is also a list of strings, and the length of A is equal to the length of B. Okay, so you can tell if given this two list of strings A and B as a match solution according to PCP. The next one is LU is reducible to PCP. As I mentioned earlier, the proof is long and that involves some Turing machine operations. And I, with that I, is the set of distinguishable symbols A1, A2 to AK that is used to select the string in A and B to make a match PCP solution. Okay. And sigma A is the set of all the string W1, W2 to WK in list A. Okay. Actually, it should be all the symbols. Okay. W1 is a string. Okay, and all the symbols in W1. Okay, and all the symbols in W2. Okay, so basically all the symbols in W1, W2, WK will be the alphabet sigma A. Okay, and then we're gonna unit I is the indexes symbols, so altogether it's sigma A. And sigma B they do the same thing, but we take these all the symbols in x1. So here x1 is a string. Okay, all the symbols in x1, x2 all the way to sk will be all the symbols. Will be the symbols included in the sigma B, and plus the indexes. Okay. And the list language is LA. Okay. As we derive a grammar GA. Okay. And from the list of A. Okay. So basically, well, the list of A looks like this. Okay. This list A is look like this. It's It's a W1, W2, all the way to WK. That's the list A. And the list B is X1, X2, all the way to XK. And WI, XI is the ice pair in the PCP AB. Okay. So WI's are strings and XI's are strings as well. Okay. And we basically the GA, the grammar A, it is defined as start with the symbol, the only variable A. Okay. Produces W1 A1 or W2 A2 all the way to WK AK. Okay, and it will be terminated by W1 A1, W2 A2, all the way to WK AK. Okay, so notice that this AI will be indicated the selection, the corresponding WI got selected. So this is the grammar GA. And similarly, we can define the GB. Okay, grammar GB is B produce instead of WI, it produces X1 B. Sorry, B A1, and all the way to XK B AK, and also the terminal strings X1 A1 all the way to XK AK. Okay, so that's the grammar B. Okay, and it can be proved that the LA obviously is context free. Okay, and the complement LA bar and LB bar are also context free. Okay, it's hard to design the context free grammar for LA bar, but we can use the push down automata. Okay, to check if the string is not in LA. Okay, then we're gonna accept. Okay, so that can be done using the push down automata, and we know push down automata is equivalent to context free. Therefore, LA bar is context free, and typically, for the complement of context free, may or may not be context free. Okay, for example, if G is context free, the G bar may or may not be context free. Okay. So this one, we don't have that property or closure property for the context free. Okay, but if R is a regular, then R bar is also regular. So regular language, okay, the complement is closed under the regular language. Okay, and also we have a fact that if AB, an instance of PCP, has a solution, if and only if LA intersect LB is not empty. Okay, because if LA and LB intersect is not empty, and that means you have a match. Okay, and that non-empty strings will be the match solution. So that means that you have let's say you have W1, okay, and W1, and then W3, okay, and then W2, okay. That is equal to X1, X3, X2. Then this is a match. Okay, that means you select the first pair. in AB, and the third pair and the second pair, that gonna make these two strings equal. So if that's the case, then this is coming from the LA and this is coming from LB. So the intersection is not empty, so that they have solution. Okay. Oh, I'm missing one. Then the context-free language. Okay. This guy, LA bar, union LA bar. We know the LA bar is context-free. Okay. And the union operation is closed in context-free. That means, you know, the union of the two context-free will be context-free. So LA bar union LB bar is context-free. And this is also equivalent to the complement of LA index LB. Okay. And this language, okay, this language is used quite a lot, you know, to prove a problem is undecidable by reducing the PCP to that problem. Okay. Now let's study a little bit about the relations. Okay. So this is a PQ or decision problem. Decision problem means that, you know, the problem answer is either yes or no. Okay. Cannot be something else. That's called decision problems. So that's a PQ decision problems. So if we have P is reducible to Q, okay, and this less than equal means reducible to. So if P is reducible to Q, okay, the problem P is reducible to the problem Q. It simply means that I have the yes answer to P. If only if I have yes answer to Q. Okay, and this is also equivalently you say no to P, and if only if no to Q. Okay, so the basically the same. Okay, so either case we say P is reducible to Q, and if P is reducible to Q is reducible to R, the transitive closure, okay, applies. That implies that P is reducible to R. Okay, if P is reducible to Q, implies the P bar is reducible to Q bar, and the reason is if P is reducible to Q, then the yes to P if and only if yes to Q. Okay, and the P bar is no. That means, you know, negation of P if and only if negation of Q. So it's basically taken that one way or the other. Okay, so that make it you know, P bar equivalent to Q bar. Okay, P bar is reducible to Q bar. Okay, and the complement of problem itself, it's reducible to each other. So P is reducible to P bar. P bar also reducible to P. Okay, and P is reducible to Q bar implies P is reducible to Q. The reason is that we can do this using the relation of the complement of a problem. So if P is reducible to Q bar, and Q bar is reducible to Q based on this complement, and therefore P is reducible to Q. Okay, so that's why we have this. And if P bar is reducible to Q, that implies P is reducible to Q. The reason is P bar. Okay. Actually, P is reducible to Q. P is reducible to P bar. Okay, because the complement. Then P bar is reducible to Q based on this. Okay, and therefore P is reducible to Q. Okay. So now we're gonna study the problem LG. Given the context-free grammar, the language L subject is sigma star. Okay, so this is basically the equation Q. Given the context-free grammar G, we want to ask if LG is equal to sigma star. And this is undecidable, and we can actually prove the complement of PCP is reducible to Q. Okay, and if complement of the PCP is reducible to Q, then we simply say the PCP is reducible to Q based on the previous analysis. So, and we're done. So if PCP is reducible to Q and the PCP is undecidable, Q must be undecidable. Okay. So here is that given the instance AB to the PCP, and with that LG, the grammar G, the language describable grammar G is the language LA bar union LB bar, and we know this is context free. Okay, this is context free, so we can do that. So all we do here is, given the instance of PCP, we want to create an instance of the Q problem. Okay. Now, we argue that AB has no solution. If AB is no solution, because this could be this could be, and this is actually LA, intersect LB. Okay. So if AB has no solution, that means LA intersect LB. This is MD. So this is MD. Okay. If it is empty, the complement of empty is a sigma star. Okay. So if AB has no solution, if AB solution, that means PCP bar, the negation of PCP. Okay. So if AB has no solution, PCP bar, if and only if LG is sigma star, this LG is sigma star. So this is true. And therefore, the PCP bar is reducible to Q. And this is a Q, and this is a Q. Okay, you will ask it. Okay. Now we're going to ask, given a context-free grammar G, is LG equal to empty? This is very similar to the previous sigma star. Sigma star is everything, but now it's empty. So to check if a context-free is empty, it's actually decidable. Why? Because you can remove all the useless symbols in the grammar G. Okay, if you remove all the useless symbols, then all the symbols there are useful. If that's the case, and it's useful or reachable from the beginning. Okay, then if there are rules in the LG is not empty, and so this can be computed. Okay. By removing all the useless symbols. So LG equals empty is decidable. Now let's consider another problem. LR is a subset of LG. So the question is Q is basically given a context-free grammar G and a regular expression R. And we want to ask if L sub R is a subset of LG. So this is undecidable. We can reduce the PCP to the Q bar. Okay, and reduce the PCP to Q bar. Q bar, the complement of Q means no to the question. Okay. Now, to do that, first given the instance AB, that is to the as an instance of PCP. Okay. Now we have L sub G. That L sub G equal to this spatial language G, and this is again context free. And this, don't forget, this is LA, intersect LB. Okay, and the complement of it. Okay, so LA intersect AB is the solution. So basically, this language contains everything but the solution. That's LG. Okay, now with that R, the regular expression equal to the sigma A union sigma B star. So it's basically everything. Every symbols in A in B. Okay, so it's basically everything. Okay, and this is regular for sure. And then we argue that if AB has a solution, then the LG, the Q bar, okay. Q bar is, yes, that means Q is no. Why? Because, don't forget this is the LA intersect LB, okay. So if the left hand side is everything, okay, and the right side is almost everything but the solution, okay. So if you have a solution, that means this LA intersect LB is not empty. There's something there, okay. So something there, that thing is in the right side but not in the left side, and therefore the equation to Q bar is yes, so Q is no, okay. And therefore we actually reduce PCP to a Q bar. But since the PCP is reducible to Q bar, also reducible to Q. So basically PCP is undecidable, Q must be undecidable. Now if you flip G and R, okay, now you put the R in the right side, okay, and this is actually decidable, okay. So the reason is this: if you want to check if LG is a subset of LR, so here is LG. Let's say this is LG, and this is LR, subset LR. This is LR. The outer circle, okay, is LR. So if you want to check if LG is a subset of LR, it's equivalent to check if LG intersect LR bar is empty. Okay, if they are empty, then you make sure you are sure LG is a subset of LR. So basically, this is the one we're going to use. Okay. So we slightly rewrite the equation Q to Q prime. So basically, Q and Q prime are the same, equivalent. So given a context-free grammar G and a regular expression R, we're going to check if LG intersect LR bar is empty. Okay. So Q and Q1, these two problems are equivalent. Now, because LR is regular, the LR bar also regular. Okay. And we also know the intersection of a context-free language and a regular language is also context-free. So the whole thing, this is context-free, basically. Okay. So to check a context-free language is empty is either decidable. So Q prime is decidable, basically. And Q prime decidable, therefore Q is decidable. Okay. So that's all I have. If you have questions, you can leave comments in this video. Thank you. Have a good day. Bye.